Welcome back to Pump Design Lab. In Part 2, we learned that boundary layers contain slow, low-momentum fluid near a wall. Now we will see the consequence when that weak fluid meets a rising pressure. This event is called separation, and it is one of the most important causes of real hydraulic loss. Separation, the boundary layer failure. Now we come to the most important consequence of boundary layer behavior, separation. Separation occurs when the low-momentum fluid next to the wall can no longer continue forward along the surface. It slows down, stops, and may reverse direction. The main flow then lifts away from the wall, leaving a recirculating and highly wasteful region behind. To build the intuition, let's compare the boundary layer with something familiar, a cyclist trying to climb a hill. The bicycle hill analogy. Imagine riding a bicycle downhill into a valley and then climbing the hill on the other side without pedaling. Going downhill, you gain speed easily. Going uphill, you lose speed. If the hill is too steep or too long, you eventually stop and roll backward. Boundary layer fluid faces the same problem when it must move into a region of rising pressure. In fluid flow, that uphill or downhill effect is created not by elevation, but by pressure change. Favorable pressure gradient. When pressure decreases in the direction of flow, the fluid accelerates. This is called a favorable pressure gradient. It is favorable because the pressure field helps move the fluid forward. Even the slow fluid near the wall receive assistance. Boundary layers under favorable pressure gradients tend to remain thin, attached, and stable. Adverse pressure gradient. The opposite situation is where the real challenge begins. Pressure rising in the direction of flow. Adverse pressure gradient. When pressure increases in the direction of flow, the fluid must decelerate as it moves forward. This is called an adverse pressure gradient. The near-wall fluid, already slowed by friction, must push against this rise in pressure. It is like a tired cyclist trying to climb uphill with very little speed left. The outer flow and the near-wall flow face the same pressure rise, but they do not have the same ability to overcome it. Why the near-wall fluid fails first? The outer flow has higher velocity and more momentum, so it can often pass through a moderate adverse pressure gradient. But the fluid next to the wall has already lost much of its momentum to friction. It is the weak part of the flow. When the pressure rise becomes too strong, this near-wall fluid stops first. When the low-momentum near-wall fluid finally loses that struggle, separation begins. The moment of separation. At the separation point, the forward motion very close to the wall falls to zero. Wall shear stress also falls to zero at this point. Farther downstream, the near-wall flow may reverse direction. The flow that was following the wall contour can no longer stay attached, and a recirculating pocket forms between the wall and the main flow. And once separation occurs, it is not a small local detail. It changes the entire flow field downstream. What separation creates? Separated flow is expensive. It creates recirculation, turbulence, and a large loss of useful energy. It can reduce pressure recovery, distort the downstream velocity distribution, and make flow unsteady. In pumps, this unsteadiness may appear as hydraulic noise, pressure pulsation, vibration, and a reduction in head and efficiency. Aircraft wings provide the most familiar large-scale example of this process. Aircraft wing stall. A familiar example is an aircraft wing stall. At a normal angle of attack, air remains attached over the wing surface and produces lift efficiently. At too high an angle, the pressure rise over the rear part of the upper surface becomes too severe. The boundary layer separates early, lift drops sharply, and drag rises. A stall is fundamentally a separation problem. The same physics appears in internal passages as well, especially in diffusers. Diffuser separation. A diffuser creates the same challenge in internal flow. Its area increases, so continuity tells us velocity decreases. As velocity decreases, pressure rises. That pressure rise is the purpose of the diffuser, but it is also an adverse pressure gradient. If the diffuser opens too quickly, the boundary layer cannot stay attached and pressure recovery collapses. Before entering the pump, let's look at one final everyday example that explains why controlled turbulence can sometimes be useful. The golf ball lesson. The golf ball gives a beautiful example of controlled turbulence. A smooth ball often develops laminar flow that separates early, creating a large wake and high-pressure drag. Dimples trigger turbulence earlier. That turbulent boundary layer has more near-wall momentum and stays attached farther around the ball. The wake becomes smaller, and the ball travels farther despite slightly higher skin friction. Now we can bring the full story into the centrifugal pump, where boundary layers are present on almost every hydraulic surface. Now we can bring the full story into the centrifugal pump, where boundary layers are present on almost every hydraulic surface. Boundary layers in a real pump. Now bring these ideas into a centrifugal pump. Boundary layers form on every wetted wall. The pressure and suction sides of impeller blades, the hub, the shroud, diffuser vanes, the volute, and discharge passages. Pump hydraulic performance depends not only on the main flow path, but also on how these wall layers grow and interact. Let's first identify the two most important blade surfaces: the pressure side and suction side. Each impeller blade has a pressure side and a suction side. The pressure side generally experiences higher static pressure. The suction side generally has lower pressure and higher local velocity. The pressure distribution around these surfaces is what turns and accelerates the fluid, but also determines where the boundary layer is likely to remain attached or separate. Of these two surfaces, the suction side is often especially sensitive to boundary layer separation. Suction side boundary layer. On the suction side, fluid commonly accelerates near the leading edge and reaches a high velocity. Farther along the blade, it often needs to decelerate before leaving at the designed exit condition. That deceleration means pressure rises downstream. Therefore, the suction side boundary layer often faces an adverse pressure gradient and becomes a critical separation location. The severity of this risk depends strongly on how aggressively the blade is loaded. Aggressive blade loading. If blade loading is too aggressive, the pressure change is demanded too quickly. Excessive curvature, rapid blade angle change, or high inlet incidence can make the suction side pressure recovery too severe. The boundary layer may then separate before reaching the trailing edge. The blade no longer guides a fluid in the way the designer intended. If separation occurs, it does not merely create local loss. It changes the energy transfer that the impeller was designed to produce. What separation does to pump head. Euler's equation assumes a particular change in the fluid's tangential velocity, but when separation occurs, the flow does not follow the blade cleanly. The actual exit flow angle changes, the whirl component may be lower than expected, and the real head falls below the ideal theoretical head. Separation is therefore directly connected to the gap between theoretical and actual pump performance. And we must remember that blades are not the only walls inside an impeller passage. Hub and shroud boundary layers. It is not enough to think only about blade surfaces. The hub and shroud are also walls, so they develop boundary layers from impeller inlet to outlet. These layers can become thick and interact with the blade-to-blade pressure field. The resulting flow is fully three-dimensional, not the simple two-dimensional picture used in basic velocity triangle analysis. These hub and shroud boundary layers interact with the blade passage pressure field and create a three-dimensional effect called secondary flow. Secondary flow. Pressure differences across the blade passage and the curvature of the passage can drive low-momentum boundary layer fluid sideways. This cross-passage motion is called secondary flow. It can carry slow fluid from the hub or shroud toward one side of the passage, often concentrating low-energy fluid in corners where separation is more likely. That secondary flow tends to transport low-energy fluid toward particular vulnerable regions, where low-energy fluid collects. In many impeller passages, low-momentum fluid can accumulate near the shroud and close to the suction side toward the outlet. This is a vulnerable region because the flow has already traveled through the passage, boundary layers have grown, and pressure recovery may be occurring. Local stall and recirculation here can strongly distort the impeller discharge flow. The diffuser and volute then face their own separation challenge as they attempt to recover pressure. Volute and diffuser boundary layers. The diffuser and volute are designed to convert some kinetic energy into static pressure. But because they expand the flow passage, they naturally create adverse pressure gradients. A well-designed diffuser recovers pressure gradually while keeping flow attached. A poorly designed diffuser can separate, producing non-uniform flow, recirculation, lower pressure recovery, and increased hydraulic loss. Finally, boundary layer behavior can connect directly to one of the most damaging pump phenomena, cavitation. That is the end of Part 3, separation and its effect on pumps. In the final part, we will study boundary layer control, the practical design methods used to reduce separation, improve pressure recovery, and protect pump efficiency. Subscribe to Pump Design Lab and continue building your understanding of real pump flow, not only ideal equations.